Virtual Precalculus. This new unit is about probability and statistics. And we're going to start off learning about basic statistics and the relationship it has to probability. So, in beginning to talk about statistics and probability, it's important to focus on a few vocabulary terms to begin with. Alright, and I think your book has a nice discussion of this on page 853, but it's kind of about the relationship between what statistics and probability do. In both areas, you have what's called a population, and that is a large number of people or objects for which you have information. And then you have something called a sample, which is a subset or a smaller number taken from that larger group. So populations of people are often used for this. But for this example, I'm going to use jelly beans. All right. So at one time, this thing was filled with jelly beans, and it says there on the jar that it had 49 different flavors. So if we just imagine a big jar filled with jelly beans, that could be the population. And if I was to take some out of there and just have a few in my hand, then that could be my sample. Okay, so sample, smaller number, population, larger number. And what probability attempts to do is, using all the information we know about the population, in this case 49 flavors of jelly beans, try to deduce something about any sample that we might take from it. Okay, and so for example, if I look on the back here, one of the flavors is called Tutti Frutti. So the chances or the probability of getting a Tutti Frutti flavored jelly bean, if I take one out of here at random, should be 1 in 49, okay, or just a little bit more than 2%. Because, well, if there's 49 flavors and we assume that they're all equally represented, then the probability of sampling a Tutti Frutti or a particular flavor should be 1 out of 49. All right, so that's an example of what probability does. Statistics works the other way. In statistics, usually statistics is used because the population is so large or so difficult to work with that we can't access the whole thing. If you want to find out, how many people in Madagascar, I don't know, still like Tico yogurt, you're not going to go ask every single person. There's too many people. It would take you too long. So you might ask a few people from each region and use what you learn from that to conclude something about the entire population. And that's something that statistics does. They work from a sample to try to deduce something about the larger population. So if I had a sample of these jelly beans and I found that I started eating them and that they were all sweet and most of them were light in color, and every once in a while I got a nasty one, okay, that would be an example of data that I have for my sample. Data is just like measurements, right? And those were very qualitative data. There's not really a number behind it. They're sweet. They're light in color. Okay, if I started measuring like their length and said, okay, each one is 1.2 centimeters long, that would be an example of quantitative data. All right, and I could use my qualitative data from that sample to deduce things about the population. I could say, look, every single jelly bean in the sample was sweet. So I'm going to use that to conclude that the population of jelly beans, that they're all sweet. And maybe, I don't know, 80% of the sample that I tried had fruity flavors. So I could conclude, perhaps using that information, using that data, that 80% of the population has fruity flavors. And maybe 1 in 10 of the jelly beans I tasted had a nasty flavor that I didn't like. And I could say, okay, maybe 10% of the population also has nasty flavors. So that's kind of the two-way street that is probability and statistics. Probability using knowledge about the population to deduce something about a sample, and statistics using knowledge about a particular sample, data about a sample, to deduce something about the underlying population. So that's an important distinction. All right. So let's look at example 1. Example 1 on page, there's really not anything to write down here, on page 844. And it's just talking about different kinds of data. For example, the height of people on a basketball team. and they want us to say, is this qualitative or quantitative? Well, it could be either. You could say, hey, that guy's tall, that guy is short. But if you say that person is, 180 centimeters tall and that person is 174 centimeters tall, then that would be quantitative. Tall and short is more qualitative. And then they want to know, is the data discrete or continuous? Discrete means it can only have certain values and nothing in between. But really, there's no reason why a person couldn't have any particular height. You could be 184 centimeters tall, you could be 184.2, 184.00137. There's no limit on the height of a person like that. By contrast, B says the style of B says the style of shoes worn by people. I'm going to change that. What about the size of shoes worn by people? Shoe sizes are discrete numbers. There's 42, 43, 44, 45. There's no 40 and a half. There's no 41.7, right? The shoe size is either, as far as I know, is limited to integers. It's a discrete measurement. It's quantitative, but it's discrete. And then if we said the style of shoes, well, athletic shoes, high fashion shoes, whatever, lounging around shoes, that's a very qualitative way to describe something, so that'd be qualitative data. And when something is qualitative, you can't really call it discrete or continuous. That only applies to quantitative things. The way we display statistical data is often one of the most important tools we have. So we want to talk about different ways to display this set of data and answer to the question, how old are you, from a group of young people. Now there are 30 people in the list, and here are their answers, 15, 15, 16, etc. And the first thing you can do is make a frequency table. How many people said they were 15? Well, you can see on the first row here that for the response 15, the frequency is 5. That's 5 out of 30, or 1/6, or 17%. And dividing by the total number of respondents is known as, you find what's known as the relative frequency. Okay, what about for 16? Well, 5 people also said that they were 16, so the frequency of that is 5, and the relative frequency is also 17%. And on like that. So in this frequency table, you can clearly make out that 18 is the most common answer, 19 the least. And it's an interesting way to display the information. But a lot of times we want to see the information in a more visual way, and it's nice to graph it. And that's exactly what I've done here in what's called a bar chart or a histogram. Frequency is plotted on the y-axis and age on the x-axis. And each box is just as tall as the frequency would indicate. And clearly we can see that the most common answer was 18. So how did I know how tall to make that box over 18? Well, there are 10 scores, there are 10 answers of 18, and so that box goes up to a frequency of 10. Right? So making a simple histogram or bar chart like that isn't so hard. Another way to display data is in what's called a stem plot. To illustrate this, I've chosen a different data set, not the answer to the how old are you question, but some test scores from page 847. You can see some poor person got a 32, and then here are the rest of the scores, and one person got 100. Anyway, that 32 shows up here. The tens digit is on the left side of this, on the bottom side of this line, and the ones digit is on the other side. There were no 40s or 50s. There were 3 scores in the 60s, a 63, a 64, and a 67. And you can see that the same thing has been done in the 70s, 80s, 90s, and there was one 100. And so the number of responses, or the number of test scores in a given range of 10-point values corresponds to the height of each column, and we can kind of draw a line over top of that to see that the most common scores were in the 80s, and that there was very few hundreds or anything below 60s. This distribution is skewed to the right. I should have written skewed right, not skewed left. It's not symmetric. More of the answers are on the right side of the distribution. There's another kind of distribution called skewed left, which would look like this. And then there's a symmetric distribution in which high and low frequencies are of equal likelihood. And then there's uniform, in which all answers or all values are of equal likelihood.